So, good evening to all the viewers. I welcome you to this problem solving and live interaction session for the subject engineering mechanics that is being offered by Professor K. Ramesh in the Swayam portal. So, today we'll be discussing the contents of week 6, which has to do with friction. Let us look at the first question. The first question asks, which of the following relation correctly represents the Coulomb's first law of friction? And we have been given four options where F represents the static frictional force that is mobilized. Coefficient of static friction, as we all know, it is dependent on the material pair. Whatever two materials are in contact, it is dependent on that. And then we have the resultant normal force, normal to the interface, the contact interface. So we've been given four options, and if we see, these differ based on greater than or less than symbols. So essentially we know that when a body is subjected to a force and it is resting on some floor, let us say, on some floor. Now, once we draw its free body diagram, we'll mark its weight, say mg, given that this is m, and then we have some normal force, n, and then since the friction always opposes motion, friction invariably opposes motion. So since we can see that in the x direction, since we can see that in this direction, this happens to be the only force. So given that this is in equilibrium, this has to be countered by one frictional force F. Now let the applied force be P. Now this object will remain in equilibrium till this mobilized F increases to its maximum value, beyond which it can no longer counter P, in which case sigma Fx equal to 0 will not be valid. Sigma Fx will be equal to ma, some acceleration will get induced. In such a case, the minimum value of F, in the absence of P, there is no frictional force mobilized, in which case there will be no horizontal force. So from 0, it will build up to maximum of mu s n, where mu s is the coefficient of static friction. So we can see that this option is correct. Now it needs to be understood there are two common mistakes that uh, people commit while solving problems of friction. One mistakes is that they always replace frictional force with mu s n, which is not always the case. This happens to be the limiting value. Now, if the applied force is less than this, and if we apply a friction of this, let us say that the applied force, say that the applied force P is less than mu s n, and we replace F with mu s n. What this implies is this force is greater than what was applied. That this force is greater than what was applied, which implies that the equilibrium gets violated in the opposite direction, which is absurd. Which is why we shouldn't do this. You should always see if the motion is impending and only then replace this. Okay, so this is one aspect to it. Then the second mistake is the second problem. Generally, one mistake is that we replace the frictional force with mu s n invariably. Alright, so one of the common mistakes we have discussed that we always replace the frictional force with mu s n, which is not the case. This will only be true when the motion is impending. And the second is the direction of frictional force. Now this needs to be kept in mind that friction invariably opposes, as we have seen here, friction invariably opposes the motion, or rather I should not say motion, I should say tendency for motion. So wherever there is tendency for motion, friction will invariably oppose that. So while drawing a free body diagram, we should take care that the direction of frictional force is consistent with the constraints and the physics of the problem. Otherwise, we'll be solving a different problem altogether. And let me just add this also. Invariably put N through mass center. Now we can take note in this free body diagram that we have drawn. N is not passing through the center. The line of action of N is this and the line of weight is this. There is some distance. It is eccentric. It is not passing through the center, which will inevitably be the case. Because since this is set up, the normal force has to move a little bit to the right to get mobilized to maintain equilibrium. So this distance, or any distance for that matter, we can find using the concepts of moment equilibrium. So we shouldn't directly assume that this is acting in the center. So these three things, if we take care, then friction becomes quite easy in that sense. Okay, so let us look at the second question. So we have a box on an inclined plane which is held at rest by an applied force P. The magnitude of the applied force is given to be 50 Newton. And for this box and floor pair, this pair, mu s and mu d are given to be 0.3 and 0.25 respectively. Okay. And we have been given that the mass of the box is, rather the weight of the box is 150 newtons. So what is the magnitude of frictional force developed in this state of rest is what is asked. So essentially whatever we have been doing in equilibrium is the same thing we'll be doing, except in friction one more force gets added up, whose magnitude could be known in a sense that when motion is impending, we know it is mu s. When the motion is not impending, we might have to find that. So let us draw the free body diagram of this box. Take it here. I have mass mg acting here, and then let this angle be theta. So this will come out to be mg cos theta. This is mg sin theta, and then I have P applied here. So by principle of transmissibility, I have just moved it to the other point. Now that we have resolved this mass, this weight into its two components, we should remove this from the free body diagram. So I have removed that. Now it is asked that frictional force has to be mobilized. Now we have to see in which direction friction will be mobilized, because it always opposes the tendency for motion. Now let us see what mg sin theta is. Mg sin theta comes out to be 150 sin 30, which is 150 by 2, which is 75 newtons. So this comes out to be 75 newtons, while this is given to be 50 newton in the question. In which case we can clearly see that the tendency of motion for the box is down the inclined plane, in which case we will have friction mobilize in this direction. Okay, now that friction has mobilized, is it necessary that friction is mu s n? Let us calculate this also. This will come out to be 150 root 3. So this is 129.90. Newton. In which case, if we replace this frictional force to be mu Sn, what will that come out to be? What is mu Sn? Mu S is 0.3. So into 0.3 is 38. So this comes out to be 38.97 something. This along with 50, it definitely exceeds 75. In which case, if we replace that with mu Sn, what we are saying is the box is moving that way. It is having acceleration that way, which is clearly not the case because the question says it is held at rest. So F being mu n or less than that is subjective and it should be checked in each and every question. Okay, so in friction, it is easier to generally have our axes aligned to the incline. Let me call this x dash, y dash. So here, if I say take summation of forces along x dash is equal to 0. How? Why 0? Because we have been told it is at rest. So this will give me 50 plus F minus 75 equaling 0. So F comes out to be 25 Newton. The next question asks, what is the magnitude of the maximum static frictional force? Now, one thing is, I had directly written this as this thing, and then this, when I wrote mu s n, this n I directly took to be 129, which is not a very sound approach. What we should instead do is, always we should draw the free body diagram completely, in which case this is n, and then sigma f, because when we have multiple objects, then we will see that there might be mistakes happening due to the calculation of n, in which case we should always draw the complete free body diagram and then see it. We know that this box is not going through the floor. So sigma Fy is indeed 0. So this gives us mg cos theta minus n, or rather I should say n minus mg cos theta equaling 0, in which case this gives me mg cos theta. So we know that the maximum static frictional forces can be mu s n, which is this is given to be 0.3. So this is 0.3 into what was that? Mg cos theta was 129.90, which comes out to be 38 something as we solved it. 38.97 Newton. That's fine. The next question asks, the block will slide upwards on the inclined plane if the applied force P is increased to 55 Newton. Now, currently what is applied is 50 Newton. Now, if we increase it to 55 Newton, will it slide up the plane? We can see that the opposing force is 75 Newton. So, a minimum of 75 is required to even bring the friction down to 0, and then to counter its effect, we need to apply more force for it to slide upwards. So, this is naturally not true. Okay, so let us move on to the next problem. A box resting on the floor is applied with the force system shown. So we have a box and then it's applied with a force, inclined force at some particular distance of 0.2 mm from the left end. And we have been asked what is the magnitude of the frictional force mobilized between the box. This might look very simple. The idea behind choosing this problem is to identify, or rather to calculate, the position of the forces acting. Basically, primarily the normal force. You need to calculate that. So we have a box like that, and then I have a force acting like that. So let me take this here. Now I have my mass acting like that, which is 5.5 G. G I will substitute later. And from the floor will be offering a reaction force. But as we discussed, we should not put this at the center. We should put this somewhere offset like that. N. It doesn't matter if I put it here or here, because of principle of transmissibility, I can always shift it along its line of action. Let me put it here. Okay. So this is N. And then I can resolve this force into two components. Let us say that my X, it is given. It is given. So let us take that itself. Let us take this to be X, this to be Y. Now this angle is given to be 60 degrees. In which case I can resolve this, call it P. I can resolve this P into rectangular components. So I'll have this as I'll have this force coming out to be 30 cos 60, and then I have a vertical force which is 30 sine 60. Since it's not an unknown, let me not call it P then. Okay. Is the free body diagram complete? We have to account for the frictional force. Now we can see that in the x direction we have only this force applied right now, which implies that the acceleration would be, or the tendency of motion will be towards the right, in which case we need to replace this with a frictional force like that, and let me call this F, not to be confused with mu Sn invariably. Okay, and then I'm sorry. Yeah, not to be confused with mu Sn. Now let us mark this distance, or rather let me mark it here. Let this distance be d, which we will find out. Now this is a body that is in the plane of the paper, is a planar system. So we have three equilibrium equations at our disposal, namely sigma fx equals 0, sigma fy equals 0, and sigma m about z equaling 0. So sigma fy equals 0 gives us minus 30 sine 60 minus 5.5 g plus n equals 0, or n equals 30 sine 60, which is 30 root 3 by 2 plus 5.5 g, which implies that n comes out to be 30 sine 60 yeah, 30 sine 60 plus 5.5 g, which is 79.935 Newton. Now, needless to say, this n and this n are different. This is the normal force that is being applied. This is the unit of force. I take it that it's clear, but just in case. Fx equals 0 implies that 30 cos 60 minus f equals 0, or f equals 30 cos 60, which is 30 by 2, which is 15 Newton. Now we have got the frictional force magnitude to be 15 Newton. We can just cross check if this is satisfying the Coulomb's law of friction, which implies F is less than equal to mu s n. So n we know, n is this, and then mu s we have been given as 0.3. So 79.935 into 0.3 gives us 23. This is definitely less than 23.98 newtons, in which case this is correct. So we have got the frictional force mobilized as 15 Newton. So I take it that this is clear. So let us move on to the next question. A box is pushed against a vertical wall by a force P as shown. So there is a box and then we have it is pushed against a wall and it is being pushed. What must be the minimum force P so as to prevent the box from falling? So this is the clue to identify the friction direction. So basically we have the box here and then I have a force acting like that. Acting like that. So let me bring it here. Let me blow it up a little bit. Okay. Now for the free body diagram, I know this is 7.5 g, which is the weight. This is P, and this angle is given to be 125 degrees. Okay. Since this is being pushed against the wall, so I'll have a normal reaction. Let me not put it passing through the centroid. Let me put it somewhere over here. Oh, by the way, in the previous question, we didn't calculate D. We didn't calculate D. So we'll look at it after this problem. So let me call this N. And then since this is the nature of motion or the tendency of motion is such that this is preventing it from falling. Even if P were a little less than its minimum value prescribed that we need to prescribe, even if it were a little bit less, the box will be sliding downwards, which implies that the direction of friction is to oppose that, and this happens to be Fs, or rather F. Now in this case, since we need to find the limiting condition, that is the minimum force, now we can see that P, a component of P and F are the only thing that are preventing it from falling down. F we know maximum it can mobilize up to mu s n, we know. So in order for us to find the minimum P, we naturally need to take this to its peak and then calculate what is the force required for it to prevent it from falling, such that even if this reduces by a bit, this has already reached its peak and then there is no other force to counter it, in which case weight will take over and pull it downward. So for this condition, the minimum force required to prevent it from falling, definitely we will replace F with mu s n, as opposed to the previous problems that we have seen. So this is definitely mu s n, where mu s is given to be 0.26 in the question itself. Okay, so let us go about doing that. So we have sigma fx equaling 0, which gives us n plus p cos 125 equaling 0. Now it should be kept in mind that this 125 is with respect to the positive x. So if we naturally resolve this p like that, then we should put a minus sign here. Since I'm not resolving, I'm considering that the angle, the cosine of the angle will take care of that. So we can see that cosine of 125 is naturally negative, in which case that minus will automatically appear. If we already put a minus here by gauging that this is so, then we should consider this angle and not 125. I hope that that is clear. So this gives me n minus, or rather, let me take it p. So this gives me n equal to minus p cos 125. which is 0.573, or let me leave it at p cos 125 for now. Okay. Now I have sigma Fy equaling 0 because it is preventing it from falling. So there is no motion as such. In which case I'll have P sine 125. I can see that sine 125 is, no matter which quadrant I take, the first two quadrants, sine is positive, which is consistent. Sine 125 plus mu s n minus 7.5 g. 7.5 g equals 0. And n I already have here. So I can substitute this into this equation. Substitute it here. So we'll have P sine 125 plus mu s is 0.26 as given in the question. So I'll take this to be 0.26 into minus P sine cos 125 equals 7.5 g. So from here I can, so this I can simply solve for P now, which gives me P into sine 125 minus 0.26 cos 125 equals 7.5 g, or P is nothing but 7.5 g by this quantity. 7.5 g by this quantity. So let us calculate what that comes out to be. The sine 125 minus 0.26 cos 125 into 7.5 g. This comes out to be 75.99 Newton, or nearly 76 Newton. So this is the minimum P required to prevent the box from falling. Now the question could be asked in another way, is that let us say this is the bare minimum P that needs to be applied, which I have applied. Now if I keep on increasing this P, what will eventually happen is its component this way keeps on increasing, and once that counters this 7.5 g, friction will go on reducing to 0, and then friction will become will start acting in the opposite direction. So if I go on increasing P, eventually I'll reach a case where friction and weight are actually keeping the box from moving this way, moving up the wall. So that could be another problem that can be coined. So in essence, one can ask, to maintain equilibrium, what is the range of this force I should take? Now I can see that in such a case, when only friction opposes its direction, if I keep on increasing P, how can I calculate P max? All I need to do is take this to be positive, because that is how the equations have been derived. So P max to prevent it from the box from sliding up the wall is nothing but this quantity with its sign changed. with its sign changed. Let me highlight this also. So that comes out to be sine 125 . This comes out to be 109.881 Newton. So this is my P max. This is my P max. So therefore, to maintain equilibrium, I have equilibrium in any direction, meaning equilibrium in the y direction, be it upward or downward. I need 76 Newton P. This is less than 109.81 Newton. So this is my workable range for P. This is the workable range. If it exceeds or if this condition is violated for P, then static equilibrium is no longer holding good, in which case there will be some acceleration. So I take it that this is clear. Okay. So let us look at the next question. A uniform ladder weighing 12.5 kg is leaning against a vertical wall. So we have this wall and then we have the floor here. So this ladder has a point of contact at A. This ladder has a point of contact at A, then a point of contact at B, and it is leaning against this wall, which is 4.5 meters. This slope is given to be 1 and 1, which implies that this angle is 45 degrees. Mu s is given to be 0.25. And then the coefficient of friction for all the contact surfaces is 0.25 is what is given. Now we have been asked, what is the magnitude of maximum force in Newton that could be applied in the plus x direction? That is plus x, meaning this direction. What is the maximum force like that? Some force that can be applied at point C without moving the ladder. So we are just taking one force and applying it at point C like that, such that this ladder doesn't move. So what is the maximum force that can be applied without moving is what is asked. Now let us see the free body diagram for this problem. I'll draw the ladder as a line rather than a three-dimensional or two-dimensional object. So I have this applied at 0.8 meters. So this is 0.8 meter. And then I have the weight that is acting is 12.5 G. That is acting at the center of the ladder. So let me take this here. Now the most important thing in analyzing friction problems is drawing of the free body diagram with the correct direction of friction. Once that is done, rest is simply an exercise of doing sigma fx, sigma fy, and sigma m equal to 0 to calculate all the other components of forces. So it all depends only on how you draw the free body diagram, whether it is capturing the physics of the problem correctly with respect to the direction of friction or not. So essentially, we should be practicing drawing only free body diagrams. Rest is just a straightforward algebra, which we have been doing till now. So the focus would be more on drawing the free body diagram. Okay, so now here I have a normal force, call it NB. And then here I have another normal force, call it NA. Now I can see that if I keep on pushing this, ladder here, eventually the ladder is like this. The next it will try to go like that, and then it will go like that, and so on. So the nature of motion, the tendency of motion for this ladder is this way. It is from here to here, which implies that friction is acting in this direction. Friction is acting in this direction. Now we have been told what is the maximum force. So we are looking at the limiting condition naturally, in which case all the friction mobilized is reaching its maximum. So this will be mu s, which is 0.25. This will be 0.25 NB, and this comes out to be 0.25 Na, because mu s is 0.25. So have we accounted for all the forces here? Yes. We have accounted for the force that we are applying at C. The distance of C is given to be 0.8 meters. And then we have the weight of the ladder, the normal force, and then the frictional force with the correct direction gauged from the physics of the problem. So the free body diagram is complete. Now it is just a matter of solving sigma fx, sigma fy, and moment equaling 0. So let me copy this and put it here. And by the way, this distance is this distance is 4.5. This is given to be 4.5, so that will be 4.5 by root 2, because this angle is 45 degrees. So I'll just mark it here, 4.5 by root 2. Let me put it in some other color. So we have our free body diagram complete now. Okay, so let us take sigma fx equaling 0. That gives us F. What are the forces in the x direction? This is 1. And then we have this force next. And then we have Na. Nothing else. So F minus 0.25 NB minus Na equals 0. So this is one condition we have got. Next is sigma Fy equaling 0. We can see that this is in the y direction, this is in the y direction, and so is this. So these three will appear here. So I have NB minus 12.5 G minus 0.25 Na equaling 0. Now I can see that I actually have three unknowns here, Na, Nb, and F. These three happen to be the unknowns. So I need at least three equations to solve for this. Since I have moment equilibrium also at my disposal, let me go ahead and apply that. Now let me apply moment about a point where I can eliminate unknowns easily. I can take it about any point in space. Let me take it about this point, A, this point. So I can see that this frictional force will create a clockwise couple there. NB will also create a clockwise couple there. For NB, this is my lever arm. For this force, this distance will be my lever arm. But since this angle is 45 degree, this happens to be the same as this distance, which is 4.5 by root 2. Then I have this F creating a anti-clockwise couple there and anti-clockwise moment there. And then I have my weight will also create a anti-clockwise moment there. So let us take at point A to be 0. So this will give us, let me put it here rather. So this gives me minus NB into 4.5 by root 2, because this is in the anti-clockwise or rather clockwise direction. And then I have the contribution 0.25 NB into this again. Now I have the contribution due to force F, which will come out to be this distance. F is acting like that. So this distance. That distance will be total this distance minus 0.8, which happens to be 4.5 by root 2 minus 0.8. So far we have accounted for the three contributing forces to the moment. Now only force left is this weight. So that weight will also create a clockwise couple, anti-clockwise moment, which is 12.5 G into, since the weight is acting at the center, which means this will be my lever arm, which is half of 4.5 by root 2, which is nothing but 4.5 by 2 root 2 equals 0. Now I just need to arrange these equations. So let me just put these equations here, copy them again. Equations of equilibrium are, this is one, this is the next one, and this is the third equilibrium equation. So I have three equations and three unknowns. So I can basically solve this by putting it in a matrix. So let me go ahead and do that. Let me move it here such that I have Na, and then I have Nb, and then I have force F equaling some vector which comes here. Now it's just a matter of populating this matrix. So we know that this will be 3 by 3 and this is 3 by 1. So this will give me 3 by 1. So what is the coefficient from the first equation? What is the coefficient of Na? It is minus 1. So I will put minus 1. The coefficient of Nb from the first equation we can see is minus 0.25. So let me put minus 0.25 here. The coefficient of F is 1. And what is the right side? It is 0. So this first equation we have captured by this. So let us go ahead and capture the second equation. I can see the coefficient of it will be minus 0.25. For NB it will be 1. And then F doesn't appear in this equation. So the coefficient would be 0. So this is minus 0.25. NB is 1. And this is 0. Equaling. So we need to take this to the right side. So it will lose this minus sign. So it will be 12.5 G. For the third, for NB, for NA first, NA doesn't appear because we have taken moment about A. You remember moment about A. So naturally NA will not appear here. So NA's coefficient is 0. NB, we can see that these two terms are having NB. So essentially it will be the sum of these coefficients. Sum of these coefficients. So let us take it from here. I shouldn't forget the minus sign that was there. And then I have minus 0.25 into this thing again. So this entire thing is my coefficient for NB. here if I take NB common. And then for F, I have this as the coefficient. So let me go ahead and put it here. And then I take this to the right hand side. So it becomes negative. That is what I need to substitute there. So this will come here and then it will be negative because I have taken it to the right hand side. So this is my matrix, coefficient matrix, and the force, rather the known vector. So let me simplify this. This will come out to be minus 1, minus 0.251, and then minus 0.25100, 0, minus 4.5 by root 2, minus 0.25 into 4.5 by root 2, 4.5 by root 2 minus 0.8. So this comes out to be, these two terms come out to be minus 3.9774, and this comes out to be 2.3819. 3819. And let us go ahead and solve this also. 12g into 4.5 by 2 root 2. 12.5 into 9.81 is 4.5 by 2. So this comes out to be, just replace this with the actual value, which is 122.625. And then the third value is minus 195.0, or rather 10. Okay, so now it is just a matter of matrix inversion. So what will this come out to be? This is equal to, this is equal to this inverse of this into this vector. So what does that come out to be? Let us see. A inverse B is 142. Yeah, okay. So this comes out to be 142.93. This is 158.35, and this is 182.52 Newton. All are forces. So let us go ahead and look at the question, what it is asking. What is the maximum force that can be applied in the plus z direction so that if the ladder doesn't move? We took that force to be F, and F has come out to be 182.52. So we have this as 182.52 Newton. What is the normal force at A mobilized when this maximum force is applied at point C? What is the force mobilized at B when this is so? So these two forces we have got here, NA and NB we have got. This is NA, this is NB. NB, NA. F max, NA Newton, NB equal to 158 Newton. So we have got all the answers here. Okay, now let us look at the next question it is asking. It is asking, is it possible to overturn? It is possible to overturn the ladder about point B by gradually applying a load at C in the negative x direction. Is it true, false, or it is insufficient to conclude? So let me take my free body diagram from here and then just make the changes there. So let me copy this. Now this happens to be asking that this is point B. Let us be clear about it. This is point B, this is point A. Now it is asking, is it possible to overturn it about point B if, let us say, that I took a force and applied it at point C like that. I took a force and applied it like that, and it is asking me if it is possible for me to overturn, meaning the ladder is like that. Is it possible for me to get these configurations? Whether it is possible. So let us look at the limiting condition when this force is applied in such a way that the contact is lost at this point with the wall. That is the limiting condition. It has not come away from the wall. It has simply lost contact. It is at that instant we are analyzing this. So in such a case, Na would no longer exist, and so won't friction. Why? Because friction also is a contact force. When there is no contact, no friction. No contact. Or rather, just, I should say, just lost contact. Now it has just lost contact. Now, is the free body diagram correct? Now we have taken force to be acting like that. Nothing is there to oppose this. It has lost contact. Naturally, NB will be like that. That is the normal force. Weight is also acting in this direction. But the frictional force, if we see, frictional force will no longer act in this direction. Frictional force will try to oppose this motion. So frictional force will be acting like that. Call it some F. We don't know. Right now we are looking at the condition where we are trying to overturn this about the point B. Let me call that F. Now, if the equilibrium is satisfied in this condition, then it is naturally possible for me to overturn this. So let us see if equilibrium is satisfied. Now that we have lost contact here, it says that the contact is lost. So now we need to take moment about this point in order to find what should be the F that I should apply. Let us first see what is sigma Fx equaling 0 give us. It gives us minus F plus F, or rather small f, equaling 0. Or the mobilized frictional force is equal to the force that I have applied, because there is no other force in the system. Let us go about assuming that this is so. Now I can see that sigma Fy equaling 0 gives me Nb minus 12.5 G equaling 0, because at A, it has lost contact. So Nb comes out to be 12.5 G, which is 122.625 Newton. So far, so good. Now let us take moment about B and equate it to 0, considering that we are overturning it and it is just at the verge of, it is just at the position where it has just lost contact with contact at A. So naturally F will have this as the lever arm and it will create a anti-clockwise moment. The weight will create a clockwise moment with this distance as the lever arm, which we saw it is 4.5 by 2 root 2. B is where we are taking the moment. So naturally these two won't appear there. So let us go ahead and do that. Let me take a page here. Let me take moment about B equaling 0. So this gives me plus F into 0.8 minus 12.5 G into 4.5 by 2 root 2 equaling 0. Why equaling 0? We take it that this configuration is possible and it is in equilibrium. Let us see if it gets violated or not. We are assuming that this configuration is possible and we are equating it to 0. From here I can calculate F comes out to be 12.5 G into 4.5 by 0.8 into 2 root 2. So what is the force I will have to apply to achieve this configuration? 12.5 into 9.81 into 4.5 by 0.8 by 2 root 2. So this is 243.87 Newton I have to apply. This is what my assumption gives me, that this configuration is possible when you apply 243.87 Newton. Now the problem arises, let us say I keep on increasing this. If I keep on increasing this force, I can see that if F increase, small f, capital F increases, then naturally small f also increases. There is no limit to F I can apply because that is by applied by an external entity. Whereas from the physics, F has a maximum limit of mu s n. This cannot go beyond that. If it goes beyond that, then sigma fx is no longer in equilibrium, in which case this will reach its peak, and if I keep on applying, it will start sliding here. So this is governed. F I have got from my analysis taking that this is holding, whereas it is limited by F max. This quantity is limited by F max, which is mu s n. Now we have got n to be 122.625 newtons. So F here comes out to be 243.87 Newton. And what is F max? F max is mu s n b, which is 0.26 into 122.625. So we can see that comes out to be 31.88 Newton, which is clearly a violation. So F is not less than equal to F max. Therefore, this will no longer hold good. As soon as we apply, keep on increasing this force from 0 to 31.88 Newton, this will start sliding here. This will never lose contact. So it is not possible for us to overturn this. So this is false. It is not possible for us to overturn this in this configuration. How will it become possible if we were to take a very rough floor where mu s is too high? In such a case, there could be some configuration where it might be possible. Okay. So let us look at this question. 3 blocks are placed over each other at a plane inclined at 30 degrees. So we have a plane that is inclined at 30 degrees. And then we have 3 boxes placed like that, out of which the top box is clamped to the wall with the help of a string, a massless inextensible wire. Okay. Now for the box, because A, B, C could be made of different materials, and the floor again is a different material. So in each of the interface, we have a change of mu. These happen to be the same, but essentially these two are different from this mu. So that is what we need to keep in mind. The coefficient of static friction for the three pairs of surfaces. This is one pair, this is second pair, this is the third pair. So for each pair, the coefficient of friction are given in the figure itself. A force P is applied to block B. So this is the block B. A force P is applied like that along the incline, parallel to the incline, so as to pull it out such that block B is at the verge of motion, is what is given. So what we are saying is at these two surfaces, the peak friction has reached and it is at the verge of motion. P is applied such that it is at the verge of motion. Now this is specified in the question that block B is at the verge of motion. If it was not specified, then how do we go about solving it? We will see that which is just, this happens to be a subset of that case. So we will see the more general condition. First thing is analyze what are the motions possible. So for that, first let us draw the free body diagram again. Let us take this to be box A. And then I have this as box B. Let me color it in some other color. And then I have box C. Maybe red. Okay. And then I have a string like that. And then I have a force applied like that. So for the combined unit, this is my, when I isolate it from the joint, naturally I have a tension here. So this is the entire unit I have taken with this as 15 kg. In fact, why don't I add a page, and what I'll do is I'll bring it here and draw it big. Let me take it here, draw it big. So this is what it is. The angle is 30 degrees. Now let us separate. Now when we apply force P, there are two possibilities. Two possibilities for motion in general. Not which not considering this comment which is made in the question that B is at the verge of motion. If it was not given, let us see what will happen. There are two possibilities of motion in general, which are: one, box B alone pulls out. So this box is like this. It'll it'll just pull out like that. It'll just move like that. That is one possibility. So this is the first possibility. Second possibility is box B and C slide along the floor. If the friction here is enough to counter, then naturally there is a possibility that both might move together. So the first possibility is, let me take it like this. So what happens? This is the free body diagram. In the first possibility, box B pulls out like that. This is my first possibility. And then let me take the second possibility, second case of motion. If I take this, what will happen is these two would have moved like that. This is my second possibility. Now the question says this is true. Question is considering this possibility, which implicitly implies that question is not considering the second possibility. It takes that the second possibility cannot occur. Let us see if that is the case or not. Let us see if the question is properly posed or not. So we will proceed with what the question says, and then finally check whether this possibility gets violated or not. Okay, so this is the free body diagram. Let me copy it once again, put it here. Now I am considering the first case. So let me separate out each of the boxes. So it's like this. This is one, this is the second one, and this is the third one. Free body diagrams. Now, since in both the possibilities, we can see that the green box is held to the tied to the floor, tied to the wall, and there is definitely motion impending on the interface. So definitely there is force like this, and then we have a normal force somewhere over here, which is NBA, which is applied from box B to A, NBA, and this is mu AB NBA, where mu AB is the friction for that interface. And then I have my weight acting like that. Actually, weight is acting like that. I'll take one component acting to be like this, which is equal to what is the which is equal to MAG, and we know that the angle for the question is 30 degrees, so we will directly apply this 30 degrees everywhere. So this is 30 cos, this is MAG cos 30, and then I have a force like that. Let me remove and draw this again. It's like this. I have one tension, and then I have a force like this. This force is mg, rather mag sine 30. Now my free body diagram is complete here. Now on to the second box. If I start drawing it, I'll have this just getting opposed because of Newton's third law. So naturally this will be mu AB n BA, and then I have this like n AB, but NBA equal to minus n AB from third law. We know this. Okay, and then I have the mass acting now, the weight. So it will be, what is the mass of block B? MB G cos 30. I have this as MVG sin 30, and then I have some frictional force. here and a normal force here. Let me consider this color for the normal force, NCB. Now, since the question says that it is at the, and we are following the pretense that this is indeed the case, so we will replace this force. We will replace this as mu BC NCB. Since we are considering the first possibility, that is why we are replacing this. So this needs to be understood very, very clearly. This is very important. Only when this is the case, we will take it. Otherwise, we will simply put it as F1. I take it that that is clear. F1 or F whatever, FCB, something like that. Now I have the force acting here, which is NBC. Third law. Then I have some N from the floor. I'll just call it NC. I don't need to put a subscript for the floor. That's fine. Since that is pushing it in this direction, so there will be friction like that. And this will be mu BC NCB. This NCB, NBC could be confusing. You can simply replace it with N1 or N2 or N3 also. So I'm writing it with different syntax with the Newton's third law also written here. So if you don't want to write this Newton's third law, you may as well take one single index and write it. Okay. Now, if this is going this way, yeah, we have to label the weight. So its mass will be, this force will be mcg cos 30, and then I have this force as mcg sin 30. There is only one more force left for box C, which is the friction force. Friction actually will be acting in this direction. Let me draw it in this color. Friction will be acting in this direction. Now this force, we take it to be F or Fc. This is important. Now for possibility 1 to hold or happen, Fc must be less than, not equal to, it should be less than mu C NC, where mu C is given to be 0.4 in the question. This, I was just thinking about what subscript to put. This mu into the total normal force here, that is the maximum friction that can be mobilized at this interface. If that mobilized friction is greater than what is coming out as the value of F, then that implies that the third box C, is indeed at rest. And our possibility 1 is the motion that will happen, meaning box B only will pull out. So we have to see that this box will only pull out when this sticks to the floor. That will only stick to the floor when the frictional force there is not exceeded beyond the maximum friction that can be mobilized there. That is what we are checking. If that gets violated, then the question is ill posed. So if you find a question like that where this is getting violated, you can definitely post it in the forum. If the question is ill posed, it is not correct. Rather, if this is strongly mentioning that this is the case, then it implies that that check must have been made there. If the check was not made there, what is the general way to pose the question? They will just say analyze this system and tell us what is the maximum force P to induce any kind of motion. In which case we need to consider these two possibilities and take the least force out of these two to induce motion. Naturally, we can see that when we will be applying the least force out of these two required to generate the motion, that is what will create the initial motion. So that is clearly to be understood. Okay, this is the check we have to do. This we have to check. That we will check. Now let us go about solving each and every free body. I have this. This I'll remove. This is 30. So let me fix my axis like that at 30 degrees. Yeah, let me take this color. X and Y. Let me call those X and Y. So sigma fx equals 0 gives me mag sine 30 plus mu ab nab equals t. And if we plug in the values, let us plug in the values later. Sigma fy equaling 0 gives me nba minus mag cos 30 equaling 0. That's about it. There are only two unknowns. So tension and the normal force. So we need not go for moment equilibrium. It is redundant. Moment equilibrium will only tell us where this is acting from this distance. I have just arbitrarily put it. It will just tell me what that distance is. That is what moment equilibrium will do. Okay, from these two I have NAB and T as the unknowns. So I have MA. What is MA? Mass of MA is 15, 25, 20. It's like that. So let us write it down here. MA is 15 kg. MB. MA is 15. MB is 25 kg. And MC is 20 kgs. So this is the data we have. Further, what we know is mu AB is 0.3, mu BC is 0.3, meaning the interface of box B and C, and mu C at the bottom or mu C with the floor is 0.45 is what is given. So this also we know. This is given data. Okay, so let us quickly solve this. MA. So this is 15 G sine 30 plus 0.3 NAB equaling T. And the second one is, or let me rearrange this into a matrix equation. So this will give us minus 0.31 into NAB. T gives me 15G sine 30 So this is my first equation, minus plus. Okay. The second equation is n is 1, this is 0, and this is 15g cos 30. 1, 5. So this is minus 0.3110. So this comes out to be n AB comes out to be 127.43, 44 rather, and tension comes out to be 111.8 Newton. So this much we have got so far by solving one of the free body diagrams. Okay, let us take up the second free body, which is this. I'll copy this and add a new page perhaps and put it here. This is not needed. This is not needed. Okay. Now NAB is 127.44. So I can replace that as 127.44 here. Naturally, if that is so, this also can be replaced with 0.3, 127.44, 127.44 into 0.3. So this is 38.23. I have replaced that. Rest is simple calculation. So let us see sigma fx equaling 0 gives me P plus mbg sine 30 minus 38.23 minus this force, which is mu Pc n Cb equals 0. Let me write it a little bit neatly. Mu Cb n Cb mu Cbc and Cb equaling 0. This 1 equals 0 gives me NCb minus 127.44 minus mbg cos 30 equals 0. Now, instead of solving for matrix, we can simply solve this, which gives me 127.44 plus MB is 25, and this is 0.3. So this comes out to be 339.83 Newton. So this is what we get for NCB. Now we can plug that here. Plugging that here, we can calculate P as minus 25 sine 30 plus 38.23 plus 0.3 into 339.83. So P comes out to be 0.3 plus 38.23 minus 25g sine 30 comes out to be 17.55 Newton. So this we have got, and NCB we have got. Now we just need to take the third free body diagram. Let us take this, copy. Let me put it here and add a page. So from here, I'll remove this. I don't need all that. Mu BC, I can calculate. NCB, I know. This I know. So this quantity, naturally, I can calculate. It's just 0.3 times of that. So let me replace whatever I know here. So NBC comes out to be 339.83. So this would be 339.83 into 0.3. It is 101.9495 rather. So this is 101.95. Now let us solve for the unknowns. The unknowns being NCB and FC. FC is not to be confused with mu C NC because that is what we are trying to check here. Okay, so sigma fx equaling 0, let me move it here. So sigma fx equaling 0 gives us MC. MC is, we have seen that it is 20 kgs. 20 kg and this is 0.45. Okay. So 20g sine 30 minus FC minus, or rather plus 101.95, because this is acting in this direction, because it is being pulled by box 2, equals 0, and then sigma Fy equaling 0 gives us NC minus 20g cos 30 minus 339.83 equaling 0. So from here we can calculate Fc comes out to be sin 30 plus 101.95, just 200.05 Newton. This is what we are getting from our analysis. Let us see if this makes sense. Now we know that Fc max is mu c NC. So for that, first we need NC. So from here we can calculate NC. It is nothing but equal to this plus this. So NC comes out to be 9.81 cos 30 plus 339.83. So this NC comes out to be 509.74. Therefore, mu c NC is nothing but 0.45 into 509.74, which is Fc max is 45% of this, which comes out to be 229.38. So Fc max we have got, Fc we have got. This is Fc max, this is Fc. So we can see that Fc is indeed less than Fc max. Therefore, box C indeed is not moving. Therefore, possibility 1 is valid. So naturally possibility 1 is our box P pulling out. Box 2, this possibility definitely holds. So the question is correctly posed. If this was not the case, then it would have been the other way around. Now we can simply see that this P calculation would have to be counted by friction here and friction here. So that also we can calculate and see, but I will leave it as an exercise. And if the question were to ask, calculate P such as to so as to prevent any kind of motion, then we should analyze these two cases and then report the least out of this, which will be the limiting condition for motion. Okay. All right. So let us just report the values here. Maximum tension. So we have got the unknowns here. Maximum tension. 1 minute. Question is asking. Normal force NAB, FAB is asked. NAB is, we just calculated 127.44. So this is 127.44. This is just 0.3 times of that. Newton. So this is 38.23 Newton. And then we have these two values, 111.8. NCB, we have it here. This we have as 111.8 Newton tension. What is the magnitude of P that needs to be applied? We found that here. P needs to be 17.55. This we have found. What is the frictional force developed between, which is Fc? So this is Fc. And what is the maximum frictional force that can possibly be mobilized is Fc max. So the question is logically asked so as to make you arrive at this check automatically. But nevertheless, we have done that on our own, so that we are clear about what are the assumptions that we made, whether they are holding or not. Okay. So having done this problem, let us look at the next problem. Okay. So let us look at the next problem. Now force P is applied to a roller. So there is a roller. Change color. So there is a roller like that. And then we have one force applied, force P is applied to pull it over at point B, to pull it over the step. So essentially we have a step here and this wants to pull it over that step. So once we move that, the configuration will be something like that. That is what they are trying to say. What is the minimum value of this coefficient of static friction required between the roller and the step to make this pulling over possible? So what will happen when we pull over this? Essentially, it will lose contact at this point. So that is the entire essence of this question. So let us see what that is. Now when this happens, let me take it with the step. So I have the step here like that. So what will happen is, if I take my free body diagram, if I remove the step here, I have to put a force like that. It has already lost contact at this point, so there is no other force. Then there is the weight, which is given to be 10 kg. So I have 10g acting over here. Now there is one interesting aspect about this. This happens, now we can see that there are three forces that are applied here. Let me draw it a little more neatly. So I have my force mg like that, or rather 10g. This is the reaction force from RC. This is RC. And then I have force P applied. Let me pull that out a little more like that. This is P. Now this is a three force system. That is a body with three forces. In such a case, from principle of transmissibility, I can take this force, move it along its line of action and bring it here. That is very much possible without changing the external effects. Now having done that, if I take this, for this system to hold, it should satisfy moment equilibrium when this has lost contact. If it has lost contact at D, so it is just at the verge of losing that contact. Once it is lost, it should hold there. Only then it is possible. So for that to be possible, it has to satisfy moment equilibrium. Now if I take this force and move it along its line of action, what I see is it has to pass through this point. If it does not pass through that point, then the force equilibrium does not get satisfied. So that is the constraint that is interesting here. So my line of action should be such that has to be the line of action of RC. This has to be to satisfy equilibrium. So the line of action is actually like that. If this does not happen, then this condition won't be possible. The pulling over operation will not be possible because there is some residual moment which is not keeping that in equilibrium when it loses contact at D. Okay, now at any point, this can be resolved into two components naturally. Now what we have understood from this is, if I draw a line like that connecting point B and point C, this line is my line of action for this force RC. So naturally I can resolve this force into two components. One is radial like that. If I take my RC radial like that, which is passing through point A, meaning if I shift this, this is passing through point A. This is my force, one of the forces. This is the normal force there because it is normal to the interface. And then I have frictional force acting like that. This is my frictional force. This is normal force. This is frictional force. And this frictional force should get so mobilized that the line of action of this force, is parallel to this line. That is the entire concept here. Okay, which implies that this angle should be the same. Only then it will be parallel. Rather than parallel, I should say it should be like this. So I should move my frictional force over here. Then it will make everything clear. So this is my normal force. 1 minute. Let me erase this. Let me put this in one color. Let the total resultant force be in this color. Let the frictional force be in that color. Okay. Now let me take the frictional force and put it here, and the resultant force like that. Now we know that when there are two vectors, I have one vector like that, the other one like that, then the resultant of these two will be like that. And the resultant of these two should pass through the line joining point B and C. That is the entire concept here. Okay, so from this triangle, I know what is this angle. This is 90 and this is given to be 45. So this is 135, and I know this and this distance is the same because it's a circle. So naturally, this angle and this angle happens to be the same. So what is angle from triangle ABC? Angle ABC plus angle PCA plus 135 degrees is 180. But these two happen to be the same. These two are same. Therefore, angle B 2 times angle B plus 135 is 180 degree. Therefore, angle B is nothing but 180. 45 by 2 is 22.5. So we know now that this angle is 22.5 degrees. This we have been given. Now what we need to do is, we know this is n, and we know that this is mu s n because it is at the verge of motion. This is the maximum it can be, that the maximum coefficient of friction, that minimum coefficient of friction that is required for the maximum frictional force to be mobilized. I hope that is clear. Okay, so now what needs to be done is, we just need to calculate these quantities from analyzing the equilibrium of this body. So I leave that as an exercise for the viewers to do that, and it is not that tough. Just the entire concept hinges on the aspect that the line of action, this is the entire key to this problem, that the line of action of RC has to pass through the line joining B and point C for this to be in equilibrium. So I leave that as an exercise. So now, as we saw in problems dealing with friction, the main aspect is drawing the free body diagram correctly. Once that is drawn correctly, rest is just a matter of algebra. So let us practice, let us look at some key problems where we need to gauge certain aspects, and let us see how to go about solving them. I'll just draw the free body diagrams for these. I won't solve these completely. This is with the interest that one should know how to draw the free body diagram for the given problem pertaining to the physics asked, so that we are able to solve for the unknowns. Solving for the unknowns is simple application of equilibrium equations, so that I will not do. That is a trivial thing. The main aspect is drawing the free body diagram correctly to capture the physics. So we have a mass of, we have a rod of mass W like that, and then we have a box like this, which is on that incline, which is on an incline. So the box is like that. And then I have the cable going like that. The cable also gets connected to this. And then we have a hinge here. So what we have been asked is, what is the range of the mass of this box to prevent any kind of motion? So there are two possibilities here. One is possibility 1. The box slides up the plane, and possibility 2 is the box slides down the plane. That is, it is overpowering the link. So these two are the only scenarios. This will give us the total range, the minimum value of this box, so that it prevents this link from going like that. If this link goes like that, then naturally this is an inextensible spring, so this has to move. The box would have to move like that. So that is the minimum, that gives the minimum weight. The maximum weight is so that the weight of this system is creating a tension So that tension and the friction here are keeping this in equilibrium and preventing it from moving like that, moving down. So that is the only those are the only two possibilities. So possibility one, this happens to be the link. This is W, and then I have two reaction forces here. Let us call it OX and OY, and then I have a tension like that. Now in this case, W is known, W is naturally given. So T, OX and OY happen to be the only unknowns. So three unknowns, three static equations. So we can solve easily for them. Actually, let me draw this in some other color. OX, OY, because we know it's a hinge. So this is T, and then it passes through. Naturally, if there is some, these are given to be frictionless. In such an assumption, we are going about solving this. If these have friction, we will see next week how to accommodate that. For now, this is considering this to be frictionless. And then I have this. So I'll just take it here. Now this is the box slides up. So I have friction mobilized like that. I have my mass. This is N. I have this to be mg cos 30. And then I have one force like that. This is mg sin 30. This is the frictional force. And since we are looking at the minimum value, this frictional force is nothing but mu n. And this is that same tension. So here, what are the unknowns? Now from here, once we have solved for this, we know tension. So from here, we know tension. N is one unknown, tension is one unknown, and the other one is M. Solve for M. So this is the first case. The free body diagram for the first case, first possibility. And then let us look at the second possibility quickly. In fact, let me add a page here. So this is for the first possibility. For the second case, this still remains the same because I have the weight acting like that. Suddenly tension cannot start acting in this direction because the cable can only apply tension. It cannot support compression. So this naturally will be like that. So this still remains the same. Having the same tension, the only thing that differs is this, the friction direction. The friction direction will no longer be like that. To prevent it from falling, friction has to get mobilized like that. This will be mu n. So this is the only difference here. And this is F equal to mu1. So these two are the only conditions that we need to solve for to get the solve for M. For in each case, solve for M, and we will get the range. So this is an interesting problem that way. I don't need this page here. So let us look at this question. So find minimum mu s to prevent motion. So we have three disks like this. Which are of equal dimensions. So we have them like that. So this has to prevent the system has to be in equilibrium under some mu s. Considering that mu s is the coefficient of friction at all contact surfaces. One contact surface is this. These are all the contact surfaces, namely 1, 2, 3, and 4. So if we go about solving this, we take this free body diagram. Actually, this should be touching. This is touching actually. Okay. Now if I go about solving this, I can take this body here. I can take this body here. Now I know that in this configuration, initially this will try to move down like that. So the nature of motion, so naturally the tendency of motion here, since this moves down, the friction would try to stop it like that. I have a normal force which is radially acting. Here again I have to reverse this. So this is F, which is mu n. So this is again mu s n, and then this is the normal force. If I take this free body here, I have that normal force applied like that, which is going through the radius. So this is n. This happens to be mg. Same thing we will have here also. And I have a force like that. By symmetry, this will also be n, and this will also be mu s n. For one of the lower ones, we can just see what happens. It will be symmetrically, it just be the mirror image of the other one. So this is 1, 2, and 3. I have drawn it for 1. Let us draw it for 2. I have its mg here, its weight acting like that. And then since when it slides, this will try to move like that. The tendency of motion will be like that. So naturally my friction gets mobilized like that, mu s n, where this is my n. Now the key aspect is what happens at this point. Whether there is some friction occurring there is the whole point of this discussion. At this point, at the verge of motion, contact is just lost. Therefore, no force. Which is why at this point we don't apply anything. This is the entire key to the problem. Rest is just from geometry we can see that these three form an equilateral triangle because this is R, this is R. So this is 2R, this is again 2R, and this also happens to be 2R. So this is an equilateral triangle, which means we know all the angles are 60 degrees. So we know the normal acts at 60 degrees. Naturally, the friction will act perpendicular to that. So we know the entire configuration that way. So we can solve for mu n. Now apply sigma fx equaling 0, sigma fy equaling 0, and sigma m 0. By that, we can solve this easily. So I'm just highlighting what are the key aspects that we need to take care. For example, here, we need to realize that the contact will be lost there. For this, we need to understand that friction reverses its direction for understanding M. Now, I'll just cover this example as the last one. So, we need to find the range of force in the spring. Now, it could be so that initially the spring was like that, and the mass compressed it to bring it to this level, in which case my force will be acting like that. The other possibility is friction was the other possibility is that the spring length is only like this, and the mass has indeed brought it to this position. So the first position Let me draw the free body diagram. In the first case, spring is actually compressed. So spring force, and then I have mg sine 30. This is mg cos 30. And then I have my frictional force, which is mu s n, where this is n. Let me just take this here. Let me write spring is compressed to achieve this position. When spring is longer. Another possibility is when spring is shorter and is actually pulled. Spring is elongated to achieve this position. In such a case, we will see that it will be like that, and the mass and the friction will try to counter the effect of the spring force. The mass will try to counter the effect of the spring force, and that is how we will calculate the range, total range of the force in the spring. One is considering that the spring was indeed compressed by in order to attain this position, and the second was the spring was elongated to attain this position. So these are the two possible configurations. Okay, let me do this as the last one. So I need to find the minimum force required to induce motion is asked. Now I have a disk like that, which has contacts at point A, point B, and point A, and it is applied with a force like that. Now, how do we find out that what induces motion? So we first draw the free body diagram. I take this N A and I take this to be NB. Now, naturally, the effect of this force about its mass is to spin it like that. The motion is somewhat like that. So there will be sliding motion set up here in the opposite direction. So naturally, my frictional force here, this will be mu s NB in the limiting condition, and this force will be mu s NA in the limiting condition. And then I have my force. This is my force, let's say F. I call this F. Let this be F. And then I can resolve my weight into two components, but let me not do that. Let me just leave it like this. This is my mg. So this I have completed the free body diagram. Now there could be two possibilities. One is the force applied is such that contact at B is lost. Now I can see that I'm trying to lift. What if the contact is lost here? Then only the frictional force here is trying to counter that movement. So what I need to analyze is, first I assume that contact at B is not lost. And then I solve this configuration. And then I see if my limiting values are exceeded. If that is the case, then the contact at B would have lost. The second case would be I analyze it with the contact lost here. It is a simple free body. If I have lost the contact here and the weight is acting this way, So this happens to be the last problem. Let me just look at this. So we have been asked to describe what happens in this configuration. Now there are three boxes placed one after the other, which is in contact. And then we have the weights appropriately given. Since frictional coefficient is a function of the pair of the materials that are there at the interface, so it is quite possible that even though we have a common floor, A, B, and C could may well be made of different materials, which is the reason for different frictional coefficients. Okay, so how do we go about solving this problem? First, we take the three boxes. Let me draw this. This is just so we understand the picture clearly, so that there is no confusion later. Okay, close enough. I'll just go on to solve the physics. Now let us say these three boxes are in contact like this. First, which is the box that is overpowering everything? It is box C. So first we see that from the free body diagram of box C, I just say that this is MC G cos 15, and then I have my N, I have my weight acting like this, which is MC G sine 15, and then I have a frictional force like that, which is opposing motion, Fs. Now for the moment, let me check it with this configuration whether this N is existing or not, or rather NBC. Whether I'll first check whether this will exist or not. How I can do that? These two together have to maintain equilibrium in this direction. Along the plane, there are two forces that need to counteract and create equilibrium. I know one force has a limiting value, which is 0.35 N. This has a limiting value of max is 0.35 N. So if I take that MC, which is 30 into 9.81 into cos 15, so my N comes out to be 284.27 Newton. So 35% of that, if I take, it comes to 99.5. So this comes out to be 99.5 Newton. Fs max is 99.5 Newton. Now let us see how much of force is actually pulling it. It is 30 into 9.81 into sine 15. This happens to be only 76. This is only 76.17. What this implies is this Fs has not even reached its maximum. It is only after Fs reaches maximum that NBC will come into the picture. So NBC is naturally not there because Fs is less than Fs max, which means that this box is holding on its own. It is not supported by box B in order to keep it at static equilibrium on the inclined plane. So this box is no longer in the picture. Now we do the same activity for box B and box A and solve for what is the kind of motion that is taking place. If it so happens that for box B, the interface force is exceeded by the total force applied, that is pulling it down the inclined plane, then naturally there will be a force set up over here, in which case this entire system will have to satisfy equilibrium. So that is the way to go about solving these kind of problems. So other than that, I have nothing else to add. So we have discussed quite a lot of problems. So you can take a look at what we have discussed, and then if you have any questions, you are feel free to raise it in the forum so that we can take it from there. So I hope that I've done some justice to explaining friction today. So I'll see all of you in the next session that will be held next Friday, and we'll be discussing a bit of belt friction along with problems on dynamics, the starting of dynamics. So this actually essentially concludes the statics part. Now we will be going into the analysis of rigid bodies for dynamic problems, which is very much required for design of machinery, robotics, and whatnot. So that will be interesting. So we'll see that in the next session. So I'll see you next week. Thank you for attending.